All right, welcome back. Semantic segmentation. But before we get started, hit the like button, subscribe, share this with anyone you know taking the AWS Machine Learning Associate exam. All right, so semantic segmentation, pixel perfect visual understanding. All right, computer vision's progression from classification to detection addresses increasingly granular visual understanding challenges. Image classification answers what's in this image. Object detection extends this to where are objects located, yet neither approach satisfies applications requiring precise spatial understanding at the pixel level. Autonomous vehicles distinguishing drivable road surfaces from pedestrian zones, medical imaging systems delineating tumor boundaries for surgical planning, or agricultural monitoring identifying diseased plant tissue amongst healthy growth, right? So semantic segmentation addresses these requirements by classifying every individual pixel in an image, producing dense predictions that assign category labels to each location. Rather than returning bounding boxes approximating object regions, segmentation generates masks where each pixel receives its own classification, enabling precise spatial reasoning essential for safety critical and precision demanding applications. All right. So the architecture. All right. So the architecture of this, right? Semantic segmentation's pixel-wise classification demands neural architectures fundamentally different from those powering classification or detection. While traditional CNNs progressively downsample images to extract high-level features, segmentation requires maintaining spatial resolution to make predictions at pixel granularity. First, you have FCNNs. These are fully convolutional networks. These pioneered their approach by replacing fully connected layers with convolutional layers that preserve spatial dimensions. These networks process entire images through convolutional operations, generating feature maps that upsample layers, expand back to original input resolutions, right? So the result is a dense prediction map where each location receives classification based on learned features. Then you have pyramid scene parsing network. This is PSPNet, right? So this enhances this foundation through spatial pyramid pooling that captures context at multiple scales. By processing features at different resolutions simultaneously, PSPNet enables understanding both fine details and broad contextual relationships, critical for disambiguating visually similar categories based on surrounding context. And then you have DeepLab, right? I think we're on version 3 or 4. All right, and there's some instructions you can see. Okay, so DeepLab introduces atrous convolution, enabling enlarged receptive fields without reducing spatial resolution or increasing parameters. So this innovation captures multi-scale context while maintaining the resolution necessary for precise boundary delineation. So all three of these approaches leverage ResNet's backbones pre-trained on ImageNet and provides a robust feature extractor that can recognize universal visual patterns. And these pre-trained weights can accelerate training convergence and improve final segmentation quality through transfer learning that requires only fine-tuning on domain-specific segmentation data sets. All right. All right. So understanding segmentation masking. So segmentation data and training data requires pixel level ground truth annotations. So masks where each pixel's value indicates its category label. Unlike bounding box annotations sufficient for detection, segmentation masks demand careful per pixel labeling that precisely delineates object boundaries. These masks typically use grayscale PNG images where pixel intensities encode class identifiers, where value 0 might represent background, 1 indicates first class object, 2 denotes second class, continuing all the way through defined categories. So this integer encoding enables efficient storage while maintaining perfect spatial alignment with corresponding image input images, right? So creating these masks demands specialized annotation tools supporting polygon drawing, brush-based painting, or intelligent edge snapping that accelerates boundary tracing. And Amazon has a SageMaker ground truth, that human in the loop, to provide a managed labeling workflow that can combine automated pre-labeling with human review, accelerating annotation while maintaining quality. The label maps can document the correspondence between mask integer values and semantic categories, enabling human interpretation of model outputs and proper evaluation metric calculation during training. Let's see. And yeah, it's all deep level V3. That's where we're at. Okay. Okay, so data prep. All right. So semantic segmentation is going to use supervised approaches, right? So you basically want to carefully plan and pair your images and masks where spatial correspondence remains perfect, right? So each mask pixel will align exactly with its corresponding input image pixel. So you want to organize your training data with clear separation between images and annotations. So you would have like your bucket name slash training slash images slash object. And then you'd have your bucket slash validation slash images slash object. But you'd also have your bucket slash training slash annotations slash object, and then a validation slash annotation slash object, right? So you have to ensure consistent naming conventions enabling automatic pairing during training. And the segmentation would match the images and the masks by file name, requiring exact correspondence to prevent training errors, right? So then you create the label maps, document this, create your class definitions, and the mapping will enable proper evaluation metrics and help to interpret model predictions during inference. So let's get into the console and make this. All right, go to SageMaker AI. All right, go down to training. Click training jobs. Create the training job. All right, so we're going to name it something like semantic test. All right, and then from here, select your IAM role. Your built-in is default. And then tabular vision, clustering, time series, text embedding, text topic. Oh no, do I not see some? Oh, semantic. There we go. Okay. Semantic, you can do file, which is local, pipe, which is from the console or from the cloud environment. Select your instance type. You typically want to go for, you want to be, it's going to be intense. A GPU is going to be much more likely. So ml.p, here you go. You can do MLP 2x for the standard and probably the 5. Ooh, that might be pretty big. The 4 P4D, yeah, that might be solid for production, right? And then you're going to set at least 100 gigabytes, right? Instance count. Let's see. I want to do, yeah, no, I think this is single. Yeah, I think this is single instance. But you can have this. This is scaled to 1. It starts at 100. The scales. Okay. Keep alive period up to 60 minutes. Encryption depends on you if you're what you want. Since we're just doing development testing. But for production, you want some KMS runtime. Network isolation with the VPC. Security groups, subnets. That would be well intentioned. And then you go through your hyperparameters. All right. So your algorithm. Choose between FCN for fully convolutional, PSP for PSPNet, DeepLab for DeepLab, right? We talked about those. There's accuracy trade-offs, right? DeepLab is typically the most accurate, but it's going to cost the most. Then, so we're going to set that there. Then you want to go for backbone, all right? You basically have ResNet 50, ResNet 101. 101 has a deeper architecture with better feature representations, but it's more memory, more time, all right? Number of classes. All right. This is the distinct number of categories in your segmentations, including the background, right? So this parameter must align. So if you have 1,000 distinct categories, that's where you're going to have to go, right? Let's see, learning rate. So this is, oops, this is the gradient. Must be less than 254. All right, how about that? Okay. Learning rate. Okay. Learning rates. So start with a moderate value. This is like what we have here. The more you increase this, you get the control for gradient descent. Okay. And then let's see. Batch size. So this will be typically between, I think it's 30 and 100. This will balance your training stability with your memory. So let's set it to 48. Your epochs. Do we still have those? Yeah, there we go. So this is your training duration. Set to somewhere between 30 and 100. Set it to 40. And you configure your name, your input mode. I think we have file at top. And you select your input type, image JPEG, image.JPEG. Wrapper is not necessary for this. Compression, not necessary for this. Your bucket location, where you have your files. Your checkpoint, so if you're going to save it. And remember, you have the spot training for spot instances to save money. And your output path for where you're going to output your end results. Tags, key value pairs for accuracy for your environment, and click Create Job. All right. And at that point, your model artifacts will be saved in your S3. And you'll be able to deploy the trained models and run this with whatever you need. All right. We're going to click Cancel. And go back to wrapping up. Okay. So here we go. All right. So semantic segmentation will enable applications to demand precise spatial understanding that bounding boxes can't provide. Autonomous vehicles can use pixel-level road scene understanding to distinguish driving surfaces from obstacles, pedestrian zones, and other vehicles, right? So this is information critical for safe navigation. And medical imaging could use this for precise anatomical structure delineation, right? So you can find tumor boundary identification, organ volume quantification. So these precise measurements can inform treatment planning and surgical procedures, while you would have millimeter level accuracy. And then agricultural monitoring would be useful for plant health, right? Disease detection, yield estimation, all these things would be good for identifying affected or monitored foliage and vegetation, flora, right? And it'll support targeted intervention for whatever you need. And then you could use this for satellite or aerial analysis, right? So you could do this for land cover, urban planning, environmental monitoring, and you could have precise boundary delineation between like forests, waters, deserts, and you could incorporate developed areas and have informed decision-making for resource management, right? And then let's go to cost, right? So semantic segmentation is going to use GPU. That's going to be a major cost consideration. So this will scale with image resolution, dataset size, architecture complexity. And GPUs typically cost $1 to $6 per hour. So your goal would be to use spot instances with the checkpoint to get some cost savings. And in segmentation, with the checkpointing, would be able to do this with the checkpointing to handle the spot interruptions without losing progress. All right. And you could also consider the batch transformations for periodic segmentation tasks rather than like a persistent endpoint, which would cost a lot, right? So you do this you can do this weekly or monthly, depending on what your needs are. All right. So this gives you the ability to have production grade pixel level classification with some managed infrastructure, and that won't be fully managed by the AWS system, right? And it'll deliver precise spatial understanding for modern computer vision applications. So I hope you enjoyed this review, and I look forward to catching you on the next one. Until then, have a good day. Thank you.